In this video, I'm going to explain to you the simplex algorithm step by step by using a small problem with two decision variables that is given as follows. We have a maximization problem, so we have an objective function zeta that equals 10 times a product x1 plus 20 times a product x2 that needs to be maximized. And this is subject to three constraints, defining the boundary that is given by x1 plus x2 is smaller or equal to 100. The second constraint is 6x1 plus 9x2 smaller or equal to 720. And the third constraint is x2 smaller or equal to 60. And the decision variables are defined as being larger or equal to 0. What is fine in this problem is that it is already in the standard form for the simplex algorithm. So we have a maximization problem and we have constraints that are denoted by smaller or equal to. If we look at the graphic, we can depict it because we have just two variables where we have the x1 variable given on the x-axis and the x2 variable depicted on the y-axis. Let's have a look. Here on the lila line we have the objective function that we push outward in the solution space because it is a maximization problem. By definition we have the decision variables to be larger or equal to 0, so we are operating in this quadrant of the coordination system. And then we have our three constraints that define the solution space. And the solution space is given by everything that is below our restrictions because they are denoted less or equal to a certain right-hand side that gives our capacities in a resource allocation problem. So the solution space is given as said, but everything that is below our constraints and larger or equal to 0 for the decision variables. The simplex algorithm works as follows. We take one initial basic feasible solution and then it goes to corner point solutions of the solution space and evaluate them. By definition, it starts always in the point where all the decision variables are set to 0. That is given in this corner point of our graphic. And then it evaluates the neighboring corner point solutions. That would be this one or that one from our initial basic feasible solution. And then if it decides to go to either one of them, it evaluates also the other ones until it finds no corner point solution that is better than the one that we already have found. So the first thing that we need to do to perform the simplex algorithm is that we take just the boundary of our constraints into consideration, and for that purpose we need to introduce some slack variables that define everything that is below our constraints. So for instance, if we write this augmented form here, it is stated as follows. So I use some algebra to be inserted already in the tabular form. When we provide the simplex, then it becomes easier to see. So I put everything on the left-hand side and it gives us zeta minus 10 times x1 minus 20 times x2. And then introducing slack variables for the constraints gives us, for the first one, x1 plus x2 plus slack variable w1 equals then 100. For the second one, 6x1 plus 9x2 plus a slack variable w2 equals 720. And for the third one, it is x2 plus w3 equals 60. Now I want, for the steps of the simplex algorithm, to introduce something that is useful to understand what we are doing. For that purpose, I put the slack variables on the left-hand side of the equation and every other term on the right-hand side. So I need to put x1 on the other side and x2 on the other side for the first constraint. Then w2 is defined by 720 minus 6x1 minus 9x2. I got a little space problem here. And w3 equals 60 minus x2. As I said previously, we start with one initial basic feasible solution for the simplex algorithm that is given in the corner point. So I define the initial basic feasible solution as being the decision variables and the values for the slack variables, where I have the decision variable set to 0. And then I can read directly from what I have just written here for the slack variables. I can directly read it from the board, because if we set our decision variables to 0, then we can read the values of the slack variables directly from this board. And they are given by the right-hand side, which is 100, 720, and 60. Let's shortly introduce some wording for the simplex algorithm. We call in our initial basic feasible solution the variables that are set to 0, which are our decision variables, the non-basic variables, because they don't pertain to the basic solution, and our slack variables, which give the slack to the constraints from this first initial basic feasible solution, are the basic variables. It is useful to use just some sport allegory to this. So the variables that are non-basic are those who are sitting on the bench, while the ones who pertain to the basic solution are those who are in the team. So the first step of the simplex algorithm is now to decide, or to look at, if we can increase for some of the decision variable and gain a better objective function to it. So we have a look at our objective function, look at the coefficients, and see if we would gain something in case that we increase for some variable. So we see that we have a coefficient for x2 of 20 and 10 for x1. So if we increase for x2 first, then we get, for every unit that we increase, 20 monetary units. despite when we do the same for x1, then we just get 10. So the first good guess for the simplex algorithm would be to increase x2. Step 2 is now to ask for by how much we can increase. And once again, the slack variables will help us to decide until when we can do this. And we would perform for that the minimum ratio test. So once again, how the definition of our slack variables on this side here are useful, because we can now read from the table what would happen if we would increase for x2, in a sense that we can increase x2 until one of the slack variables would become 0. If we look at our graphical solution, we can also see what happens. So we start from the initial basic feasible solution, and we have decided to increase for x2 until it is limited by one of our constraints. And in this case, this is our third constraint who is limiting. We can also see this, as I said, from the slack variables. So if we take W1, we have given 100. Now x1 is 0, so I just write minus 0 minus x2. So we can increase x2 until 100, and then W1 would be 0. Same now for the second slack variable, 720 minus 0 minus 9x2. So we could increase x2 until 720 divided by 9, which is 80. And W3 is 60 minus x2, and we could increase x2 here until 60. So W3 is the one that would be first 0 when increasing x2. So W3 in this point would become 0 if we increase x2 to 60. And now, once again, some wording. So the third slack variable would be our leaving basic variable, and x2 would be our entering basic variable. Now let's use our tabloid for these steps. By the way, step 3 is then, I forgot that, to increase x2 until 60, which decreases the slack of W3 to 0. So we would be in the first corner point solution. If we use the tabloid now for this, then I just shortly put our coefficients in the tabloid for our objective function, and this is useful now, the version that I just denoted in the augmented form. So I can put zeta. For zeta I put 1. Now I denote the coefficient for x1, that is minus 10, minus 20 for x2. No slack variables are given for the objective function, and no right-hand side so far. And now I do the same for all our constraints. That is, for the first constraint, 1x1 plus 1x2 plus 1 slack variable, and the other two are 0, and the right-hand side is 100. Now for the second constraint, I have a coefficient of 6 for x1, 9 for x2. The slack of W1 is 0, it's not included. Slack for x2 is 1, and for the third one it's 0, and the right hand side is 720. Now for the third one, we don't have an x1 in the constraint, but one x2 and a slack of W3 and a value of 60 for the right hand side. Now looking at the minimum ratio test, it's done as follows. We have first of all decided that we would increase for x2 first. So this is also called to be our pivot column. And now we want to find our pivot element by doing the minimum ratio test. So we would divide the right hand side by the element of the pivot column. That would be 100 divided by 1 is 100. And 720 divided by 9 is 80. And the right hand side 60 divided by 1 is 60. And we see that this is the minimum value. So we take I highlight it in blue maybe, and it becomes more clear. So this is our pivot element. So the question is, how can we get the x2 to be 0 in the pivot column? And this we can do by Gauss elimination. So for the objective function, we would use the pivot element row to produce a 0. And this could be done by taking plus 20 times the pivot element row. And for the first constraint, how we can produce a 0 here for the 1 is by simply subtracting the third constraint from it. And for the second one, the 9, we can take minus 9 times the pivot element row. So if we perform this, then we get the next tabloid. Zeta is still 1 because 1 plus 20 times 0 is 1. And minus 10 plus 20 times 0 is minus 10. Now minus 20 plus 20 times 1 is the 0 that we wanted to get. And now we go on like this. We have 0 plus 20 times 0, 0. 0 plus 20 times 0 is still 0. And now we have 0 plus 20 times 1 is 20. And for the right hand side, we have 20 times 60 is 1200. Now going on the next row, we have the first constraint. We have 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 1. 0, sorry. And 0 minus 1 is minus 1. And 100 minus 60 is 40. Now the second one, the second constraint, 0 minus 0 is 0. 6 minus 0 is 6. 9 minus 9 is the 0 that we wanted. And 0 minus 9 times 0, 0. 1 minus 9 times 0 is 1. 0 minus 9 times 1 is minus 9. And 720 minus 9 times 60 is 180. And our pivot element row stays the same as we have done. No Gauss elimination here. And that was the first iteration that we have done. So in the second iteration, where we are now, we perform the steps that we have done in the first iteration one by one. So the first question is, if we increase for now x1, can we still improve the objective function value? If we look in our column for the element x1, then we see that it has a negative coefficient, and that means that we can still increase for that element to improve the objective function. This becomes also clear when we look in our original problem. And if we look in the graphical solution, then we can see that we are now here in this corner point, and if we increase for x1, we go along the line to the next corner point solution, that is the one given here. So we can in fact still improve our objective function value by increasing one of the decision variables. So once again, we define our pivot column as the one of x1, and now we perform the minimum ratio test to see which of the equations would be next binding. From our graphical solution, this becomes clear, but yeah, if we have more complicating problems, then we can't depict the graphical solution, so we would perform the minimum ratio test as follows. So we take 40, the right-hand side of the first equation, divided by the element of the pivot column, which is 1. So 40 divided 1 is 40. Then for the next one, 180 divided by 6, and this is 30. And then for the third constraint, we have 60 divided 0, which is not defined. So we don't have to regard it, or in other words, we can ignore it. So the minimum of these values is now given by the second constraint. And in fact, if we look at our graphical solution, we see that what was first the third constraint that limits x2, we have now the second constraint given by the blue line, which limits the which binds or which forms the next corner point by the intersection of constraint 3 and 2. And by the way, the red line is our constraint 1. So we use now the 6 as a next pivot element, and because that can be complicating for Gauss elimination, I divide before performing Gauss, I divide it by 6, so I have a 1 as a pivot element, and just for the sake of clearness, I reproduce the table as we had before, leaving everything equal, but not the pivot row. Yeah. And now I divide our pivot element row by 6, so I have for the x1 1 here, 0, 0, and 1, 6 for the slack, and minus 9 divided 3 is 3 divided 2, and 180 divided 6 is 30. So we can work with them. Just shortly, the third constraint has still the following coefficients. Okay. So next step is we perform Gauss elimination to eliminate the x1 from all the other constraints. And once again, how we can do it is we can take the objective function value, the objective function, and take it plus 10 times our pivot element rho, which is the second constraint. Now, how we get rid of the 1 here is by subtracting the third constraint from the first constraint, and our pivot element rho stays the same, so we do nothing. And in the third constraint we don't have x1, so we can leave it as it is. So by doing so, we have still for zeta 1, because 1 plus 10 times 0 is 1. Then here we have produced the 0, and now we have 0 plus 10 times the second one, which is 0, 0. Following this is 0 plus 10 times 0 is 0. 0 plus 10 times 1/6 is 10 divided 6, which is 5 divided 3. And now 20 plus 10 times minus 3/2 becomes then 5. And for the right hand side we have 1500, because we have 1200 plus 10 times 30 becomes 1500. So shortly now for the first constraint, 0 minus 0 is 0, 1 minus 0 is 0. By the way, I made a mistake here. That is, of course, our equation 2. Sorry for that. But everything else is still correct. So here we have 0 minus 0, 0, 1 minus 0 is 1, 0 minus 1/6 is 1/6, and minus 1 minus 3 divided by 2 is then 1/2, and 40 minus 30 is 10. Now for the second constraint we have 0. We have not provided here Gauss elimination, so we can just reproduce the coefficients of the table given beforehand. And this is for the third constraint given as follows. And now we are done. We can read our optimal solution from the table by just looking at the ones. So for zeta, where we have a 1 given, we have the optimal value of 1500 with x1 that we can read from the column of x1, which is 30, and then x2 we have given by 60. And this is the corner point where we have lately just increased for x1. So we are done now. What is interesting to see now from the tabloid of the simplex is that how could we improve still our objective function value. So for instance, if we look in the tabloid, we have given a slack for the second constraint of 5 divided 3, and for the third constraint of 5. So for instance, if we look at these two constraints, we can They are given also here by the values of the right hand side, so it's the second and the third. So these are the ones that we are looking at, and the question would be, if we increase the right hand side, which is also denoted by our BI, by 1 unit, how much more profit would we gain from that? And this we can read from the values of the slack variables in the last tabloid of the Simplex algorithm, where we have given a value of 5 for the third slack and a value of 5 divided 3 for the second slack. So if we look at the graphical solution, the question is, if we would increase the third one, now the right hand side, from 60 to, for instance, 61, that would be moving the equation up by 1 unit. We would gain a delta of Z of 5 monetary units. Whereas if we increase for 1 unit of the second constraint, where the right hand side was given by 720, if we increase that by 1 unit, that would be repositioning the second equation by 1 unit. We would have an increase in zeta by 5/3. Now a good question would be, if we increase 1 unit of the first constraint, would that have any effect of our objective function value? And once again, we can answer the question by our tabloid by looking at the slack for the first constraint, and we see that the objective, the term here is 0, meaning that this constraint is not binding. So if we increase any capacity of that constraint by 1 unit, then we would gain no increase in the objective function value. And once again, if we look at our graphical solution, this becomes fairly clear, because we can see that our constraint is, that was here, our x1, is not partaking in our optimal solution. So it's not binding with respect to our solution. And that means that increasing it further, like the other ones here, would gain absolutely no additional value to the objective function value. These slack variables of the last tabloid in the Simplex algorithm are also called shadow prices, which denotes the worth of an increase of the capacity, so of the resource of a constraint, and the value that it is worthwhile to do so.